is going to talk on nilpotence theorem by homological residue fields for Lie superalgebra representations.
So first of all, I'd like to thank the organizers for the invitation to speak here and for their hard work in actually organizing this conference. So this work is joint work with Matthew Hamill. He's my PhD student currently. It turns out there's another famous Matthew Hamill. We have a documentary on him. This is not the same one. So if you put another L after his name, then it turns out to be a very famous mixed martial art fighter. So not to be confused with the mixed martial art. All right, so I'm going to start off my talk by giving some motivation. So the first part of my talk is tensor triangular geometry meets geometric representation. So I'd like to run over a very specific example of a computation for a finite group scheme. And so here's how it goes. So G is going to be a reductive algebraic group. If you want, you can think of G being GLN. Okay, and the field is characteristic P. And then what you do is you take the Lie algebra. It's a restricted Lie algebra, and you can form its restricted universal enveloping algebra. Now, in a group scheme language, this is the same as looking at the first Frobenius kernel. So if you want to look at the group scheme G1, this is the same as the representations for this finite group scheme. And then you take the stable module category, small stable module category for A. And the theorem goes as follows. This theorem is due to, well, it's due to lots of different people. Okay? There's lots of people who actually contribute to this theorem, so it's kind of a community theorem. So if you look at SPC of KC, this identifies with the projectivization on the nilpotent cone for the Lie algebra. And here I'm going to assume that P is large enough. So P is larger than the Cox theorem. Okay, so N is here is the nilpotent cone. It's a subvariety inside the Lie algebra. So sometimes we call this the nil cone. All right, so if you have heard talks in geometric representation theory, the nilpotent cone appears everywhere in like representations of Lie algebras. And so, one time I was at a conference involving a lot of geometric representation theorists, and I was just wondering, like, where does the nilpotent cone really come from? And I was asking a lot of the participants this, and they were just saying things about how you use the nilpotent cone, but where does it actually arise? Well, it really arises from the tensor triangular geometry in the category. So this example actually illustrates that the nilpotent cone is a very, very important geometric object that arises naturally in the context of tensor triangular geometry. So I just wanted to throw that nugget out at you. If you have friends who do geometric representation theory, you can actually ask them where the nilpotent cone comes from. See if they know. Let me also mention a little bit more seriously. This nilpotent cone comes up in the work of Arkhipov, Bezirkov, and Ginsburg for the small quantum group too. And people like Julia and Chris Negron have been actually working on sort of connecting up the TTG more with like representations of quantum groups and cohomology. All right, so here's a natural question that I became interested in. So what is the geometry for the superalgebra representations? Okay, so you have these superalgebras, finite dimensional ones even. And is there any geometry behind the representations for these superalgebras? So the natural place to look, motivated by this example, is to actually look at the tensor triangular geometry for these superalgebras. So let me do that. All right, so I have to give you a brief introduction or a crash course on these superalgebras. So I'm just going to start with the most basic one. Actually, first of all, Lie superalgebra is just a Lie algebra, sort of like a Lie algebra, but it has this Z2 gradient. And it satisfies the axioms of very similar to Lie algebra, except you have to put minus ones everywhere. And it satisfies things like the super Jacobi identity. So
Can I ask if this is going to be the motivating? What is it known what happens for smaller primes at all?
Smaller primes. So this is
Just in the cox of the number,
Oh, yes, it does. It does. We have word results on that.
but it's not that answer.
No, it's a closure of a nilpotent order. Okay, I mean, they're not.
Okay.
All right, so for Lie superalgebras, let me give you the primary example. So this is GLMN. So it's basically it's a vector space M plus N by M plus N matrices. And the G0 component looks like GLM cross GLN. And it's basically they're matrices where you put things on the blocks. M by M block and N by N block. And the G minus one part naturally is just a stuff which is over here and over here. Okay. Now, the nice thing is that the G0, now I could even talk about the group now. This is a GLM cross GLN. And this acts on G1, just via the adjoint representation. Okay. All right, now what I have to do is I have to actually set up some categories for you. These are very famous categories which have been studied by lots of people. So I could define script F for you. So these are G supermodules. I'm just going to abbreviate it by G modules. And they're finite dimensional that are completely reducible over G0, over the reductively algebra G0. Okay. Now it turns out that this category is a Frobenius category. Okay, so projectives and injectives are the same. So you can actually form the stable module category. So actually, you can actually form, before that, you can actually form a category where you actually just look at infinitely generated modules. So possibly infinitely generated modules. So let me say arbitrary.
So could you just repeat again what F was again? Just the definition, just the
Script F?
yeah,
It's a category of G models.
that
That
are
finite dimensional and completely reducible.
completely reduced.
It's a category.
And excuse me, and the notation is G, comma, G0. Is it?
Yeah, G comma G0. You put a little bar.
Yeah.
Mistake putting the bars over this. I apologize. Okay, so this is Frobenius. I'm going to actually form, let me call it K upper C. I may form it later on. So this turns out to be the compact objects. And so we'll just do GG0 here. And this is going to sit inside a big category. And this is going to be big state of CGG0. And these are tensor triangulated categories.
Okay.
So they're just like the ones you would get for like finite groups. All right, so I have to tell you something about these categories. And so why don't we look at the cohomology ring? So if I look at the X in this category, I'll just abbreviate this by stripped out about that. Then it turns out that you can identify the extensions with the relatively algebraic cohomologies for the superalgebra. This is a very important point because you can actually do calculations. So this is sort of an abstract category, and you can actually do calculations with this. So when I actually put the cohomology in for the trivial module, if there's an explicit complex which computes this cohomology, it's like a causal type complex. And it turns out to be the ring of invariance on the symmetric algebra on the vector space G1 stuff. Okay.
Is that the complex numbers?
And this is over the complex numbers. So it's all over the complex numbers. So what's interesting about this is that, this is a good point, Dave, is that this is all over the complex numbers, but everything looks in the super world, it looks like modular representation there. Okay, this is a, and the nice thing is, since you're working over the complex numbers, you can use a lot of like complex algebraic geometry. Okay, so G0 is reductive. So this is actually finitely generated. All right. And then you can sort of define support varieties like you normally would. These things, oh great, everything's looking good. All right. So you say, okay, everything looks great. Support theory. I have a finitely generated cohomology ring. And then you start doing some computations and you discover the following. You discover that you take a non-projected module, so this is a non-projected Katz module. You get something true. There are non-projected modules where this support theory does not detect projectivity. Moreover, in hindsight, you actually see that the cohomology ring does not stratify. Okay, right? And moreover, when you take SPC of KC, and you go down to product of endomorphism algebra, this is not bijective. Okay. So the basic problem here is that when you take the blocks for these categories up here, they could have infinitely many simple modules. So the cohomology is not enough to sort of detect everything. And so the cohomology ring is basically it's just too small. So you have to really enhance things for things to work out well. All right, so now I need to tell you how to enhance things. So what we need to do next is we need to talk about what are called detecting subalgebras. Okay. So this is a theory that goes back to the mid-2000s. And it's due to Brian Bowe, John Kujawa, and myself. And so what we did was we actually tried to develop a theory for these superalgebras which involve local global type of correspondence. There's no correspondence yet, but at least some local global type of phenomenon. Okay, so here's the basic idea. So you have this action of G0 acting on G1. And what you do is you use some ideas from like geometric invariant theory to actually find a certain set of semi-simple points. So these are called F1. Okay, so these are semi-simple elements. Okay. And it turns out that if you can actually form at least superalgebra by taking the semi-simple elements under this process. And this F here is a certain subalgebra inside of your least superalgebra. Okay. And the F0 part is just, you just take the conjugate of this thing. All right, so let me go back to the GLMN case and show you what happens there. Okay, so for GLMN, but let me just make it easier. Let's just do GLMN, so everything's kind of square. So your F part basically looks like matrices which have non-zero entries along the diagonals of the odd blocks. Okay, so this is going to be F1. Okay, and then you take the commutator of those elements to form F0, and the F here is isomorphic to a copy of what I call XRM. Okay, so this is actually a very nice least superalgebra which sits inside of one GMA. You can do this for all these, you know, like simple classical least superalgebras. You can just do this for that. Okay, so let's see. Let's put this up there. All right, so now let me mention some theorems that relate homology for G with the cohomology for the least superalgebra. So these theorems actually hold fairly widely. Okay. So the first theorem is if you take the restriction map and cohomology. And it goes to you can just restrict to the cohomology for F, and then you can take the N invariant. So N is the normalizer of F1 inside of G0. I won't write everything out, just a reductive group. And the nice thing is you can realize this fairly concretely as an actual restriction of function. So I remember I said the cohomology identifies with the symmetric algebra and the G0 invariants. Similarly, you can just do this over here with the N invariants. And you can realize the cohomology map in terms of this restrictions of functions. And many people have seen this before in Leader. It looks very much like the Chevalier restriction theorem. Right? So if you take like a semi-simple the algebra, you take the symmetric algebra and the algebra with the G invariance, it identifies with the symmetric algebra and the torus with the Weil group invariance. Right. So this is sort of analogous to that. So in the cohomology theory, the sort of Chevalier restriction theorem in this case is actually built in. So really, really powerful thing to have with that. Okay,
This is, but what are you claiming about that map?
oh, it's an isomorphism. Thank you. Yeah, it's an isomorphism. Okay, just like with the Lie algebra case, it's an isomorphism. All right, the second thing is in the case when G is equal to GLMN, then we actually calculated the Balmer spectrum. We kind of, in some ways, we kind of got lucky because we knew that the support theory for the F would actually be detect projectivity. So we sort of started with by that, and then we just sort of argued that that was enough. And so the SBC of KC in this example identifies with n proj of the symmetric algebra on F. I think a lot of people call this a stack function. So basically, you take the n orbits on F1 and then you sort of topologize this. So it's just not a proj, but you actually have to use an n proj to enhance things. Okay, any questions on this so far?
What does n approach mean?
So you take n invariant closed subvarieties inside of there, and then you topologize. So you really topologize, sorry, n invariant, yeah, varieties, yeah, inside of here, and then you topologize. So you have a map from proj into n proj. This is all sort of done can't remember his name. I think. Anyway, there's a paper where this is actually done.
The paper of Martin Lorenz.
Yeah, Marty Lawrence, thank you very much. Senior monk. Okay, thanks, Ken. That's why we have people that can't write. Okay. All right. So the way this proof goes, I'll just be very brief about this. So the way we prove this is sort of the standard way. And so what you do is you develop a support theory which goes to the cohomology or the supports for the FF0 cohomology. And these turn out to be n invariant. And you can detect projectivity with this. Okay, so this one detects projectivity. And then there's one thing you have to prove, which turns out to be the most difficult part. You have to prove realization. And so let me put the realization statement down, which I'm going to use later on. And this is called star. So basically it says for W closed, and proj of S star, and also n invariant. There exists a compact object. It's an upper C, such that the variety. Okay, so you need sort of an equivariant version of realization. That turns out important, and what we do is we have to actually construct modules which do the right job. All right, so now how does superalgebras relate to this diagram that I've actually put up here? Okay, so that's the next part of the talk. When my student and I started working on this, we said, well, why don't we look at Paul's paper and see if we can actually understand this by using superalgebras. And one of the main things in the work of like Balmer, Krause, and Stevenson is to actually use this idea of actually getting homological primes using these tensor functors. And the nice thing is with superalgebra is you have enough tensor functors. And so we're just going to apply this machine and then see what we get. Okay. So the first thing you really need to do is you need to enhance things. And the way you have to enhance things is you have to do some stratification. All right, so suppose I have a detecting subalgebra. And I'm going to ignore things a little bit. I'm going to do KF, and this is going to be the stable Montel category for C of Fx0. Okay. So the theorem that we first proved. So, and the rest of the work is with my student. Is that KF is stratified by R. So R is going to be equal to, it's just going to be the cohomology. So that's the numbers. So KF is stratified.
And sorry, are we in jail an M case now or general?
Any detecting subalgebra. Okay, because you can sort of like, you know, they're either SL11s or Q1s or whatever. So basically we do, so in the paper that we do this part on, we look at sort of general types of detecting subalgebras, and they're very small, so you can actually.
But G is GLMN, that's what the question was.
Yeah, so okay, so in general, you can define detecting subalgebras more generally than GLM.
Okay.
So this will actually apply to those detecting subalgebras. Yeah. Now, I don't know if it works
Detecting subalgebras of what?
for these classical simple Lie superalgebras. So like
Classical.
OSP and other ones, you have detecting subalgebras.
I see.
Okay. F4 or G3, you have.
Right.
Okay, but I didn't want to like go over all that. I just wanted to kind of stick with these. But if you want to think of this as GLM, that's fine. Okay, so you have the KF is actually stratified. Okay, good.
Sorry, can I push the point a little bit?
Yes.
So for this theorem, do you need to know that R, whatever it is the spectrum of your category?
R is the spectrum of the category. Yes. Yeah, so we actually know that. So.
And the detecting subalgebras, they kind of look like elementary buildings.
Yes, yeah, they're small enough. And that's my point. Basically, how do we prove this? Well, we just use BIC. We use the techniques in BIC. Because when you take this detecting subalgebra, and if you take U of F of F0, this turns out to be just the exterior algebra on F1 stuff. Okay, so it's really close enough. And this here, the cohomology brings the symmetric algebra. So it's close enough to using this sort of BGG type of idea. Okay, that's my point. So the proof uses that. We just follow along. Nothing. So there's a nice exposition in monograph by BIC, and you just follow along.
This is the one displayed all over the place here.
Yes. So by monograph. Oh, people have to pass. All right,
17 years.
17 years.
That's good marketing.
It's worth the 17 euros. Okay, all right.
Sorry, one more question.
Yeah.
So,
Okay.
this statement is true for any detecting subalgebra that
Yes.
it's always the exterior algebra on F1.
Yeah, that's right. Thanks. Yeah, for other ones, I don't know the answer. It's a very good question to try to, prove stratification for other, these people in these categories. That's an open question. All right. Now we move on. The next one is on homological primes. All right, so the idea is that we have this stuff, we have good control over the detecting subalgebra over here. And what we need to do is we need to we need to get information to attack the problem for G. So we need to use homological primes. So to do this, we use work in Balmer, Cameron. And Balmer, Carlton, Stevens. 19. Okay, so this has been talked about quite a bit. So you take a small rigid category and you can look at the homological primes. And you have a comparison map, which goes from SPC H of T down to SPC of T. And it's surjective as long as T is rigid. So we have that in our case. Okay. All right, so we sort of know the answer already, but what I want to do is I want to actually construct the homological primes in the case of GLMF. So we have. All right, so what we have to do in order to do this is we have to set up the relative tensor functors. So let's look at X and F. Now, when I look at the universal enveloping algebra generated by this X, I can get something which looks like an elementary Boolean, but I also could get something else. And it turns out that something else is a Q1. So I either get something which looks like C of X over X squared, or I get the universal enveloping algebra of Q1. And this is very well understood. This is a binary representation type. And so, yeah, so this one has binary representation. So the natural thing to do is just consider the stable module category. This. We call this C of X 0 bar. And this is the TTC field. Include that. Okay. So now what you can do is you can actually look at the restriction functor. And this turns out to be a tensor functor because the profile is very nice.
Sorry, what do you mean by field here?
Well, it's a definition. So it's a definition of a TTC field.
And the object is tensor faithful,
Yeah,
and the big objects are coproduct of components.
Okay. So all this is language that's done in these papers. Okay, so you define pi of X, and what you want to do is you want to sort of take K of X, F down to F of X. Okay, so I sometimes we're doing this with an F up on top. And up in the lemma over here, notice that I have a box up there. So the little box up there could be F or G. Okay. So you can insert F or G into the little box. Okay. All right. So I'll just put up this diagram next. And
Is U of Q one is an algebra?
as an algebra.
Yeah.
So Q1 is just a two-dimensional Lie superalgebra. And so the relations are, let me get it right. So Q1, it's going to be T direct sum X, all right? So X bracket X is exactly equal to T, and T bracket X is good. And then you just take the universal and go. Okay. In fact, the algebra, the stuff generated by T is an ideal. Okay, so I have this diagram that I have put up before. So this is a KF compact. This goes on to FPC of K. And then we have comparison maps here, which go to proj of the endomorphism algebra. It matches the cohomology ring. And then we have the map data that goes back. So this is described in Kent's talk. And so we know that these are eta and rho are isomorphisms. Okay, so you can prove those directly by just using standard arguments because these algebras are so small. And then what you can do is you can actually use the stratification theorem to show that this is actually an isomorphism too, at least a bijection. So you can use stratification. And then the argument in Paul's paper using pure injectors if you want to show that you have an isomorphism. So SPCH. FC, the isomorphism. Okay, so everything in sight works out for detecting subalgebras. A lot of times we call these, we don't call them pi points here, we call them Q points. I don't know if that'll ever stick, but for superalgebras, you may get something different than something which looks like a pi point. Okay, great. Okay, so last part of the talk, I need to use this diagram to actually make everything work. Let's do that. All right, so use nilpotence. All right, so we have a natural restriction which goes from here to here. So you can take modules in here and you can switch them to modules in here. Then we have this stable category for x. We have this pi x of g, and we have pi x of f over here. Okay. Now with these tensor functors, you can use the big machine up here to create these homological primes. Okay, so that's what this machine does. You sort of plug in an x, so an x could be in that one. Over here, you take this tensor functor over here, you apply this theorem in B case, and then you get B of x. You get this homological prime. Okay. So Bx is a homological prime associated to this pi x of b. Okay, and then when I put a prime up here, this is for f. Okay, so this is a homological prime associated to pi x of f. Okay, and then once you have this, you have a homological residue field, which goes up along the top diagram over here. Okay, so this is H bar, P of X, and this is the homological residue field corresponding to P of X. And similarly, when I put a prime up here, the homological residue field corresponding to P of X with a prime. Okay. All right, so now what we have to do is we have to sort of tie in the nilpotence theorems for F with nilpotence for G. So we have to do next. So I think I can stay here. So here we go. All right, so the first thing is you let F be a map from a compact object to an arbitrary object. So this is in KG, KC of G, and Y can be any sort of object in KG. Okay. All right, so there are 4 points that I'm going to make, and then ultimately at the end, I'm going to actually state sort of nilpotence for the order. All right, so the first thing is, if you take H bar B of X, and if this is going to be 0, then you can actually diagram chase with this setup over here and show that H bar B of X of the restriction of F is actually equal to 0. And this is over a prime. Okay. All right, so you take 2 diagrams for F and G, and you sort of look at them and put them together, and then you see. Okay. Second point. So we know because stratification, we actually can say the following. So if this HP of X is 0 for all X in F1, so remember these give you, and these should be primes. Oops. So these give you all the homological primes for F1. So this implies the tensor nilpotence. This is my Balmer. This is the Pearson Paul's paper. All right, now what we have to do is we have to get from F to G. And this is the tricky part, which I'm still working out some of the details on, but I think it's right. So here's point number 3. Okay, so if I take F from X to Y, then F is tensor nilpotence, and K of G, if and only a restriction of F from X to Y is tensor nilpotent in K of F. Okay, this is what I was asking. Okay. All right. So this direction is not hard to prove. Okay. The 4 direction is not hard. It's the other direction which needs work. And the other direction actually uses recent work of Serganova and Sherman. And for this detecting subalgebra over here, it turns out that the trivial module is a summand of the induction functor from F to G of C. So they actually have to use some geometry to actually prove this. And with this, you can actually prove projectivity statement saying that if you have a module which is projective over here, so you start with that module for in G, but when you restrict it, it's projective over here, it has to be projective. Okay. And then some work I've done to make policy, which ties in tensor nilpotence with projectivity. Okay. All right, and now what we do is we put everything together. So this enables us to actually get a nice class of homological primes to detect projectivity over the big algebra. So we put everything together. Or put everything together. And so let's call it script app to be equal to these homological primes that arise from F1. And the thing is, N actually is going to act on this. And so it's enough to just take orbits. So if I know that H of H bar is going to be 0 on B of X, I know it's going to be 0 also on an orbit. So this is, remember, this is N invariant. Okay, so the action of the group acts on this thing. And then what do we know? You know, that H bar B of X of F equals 0 for all C and F implies that F is tensor nilpotent. Okay, so we just apply 1 to get to down to F. Okay, so then we know down at F, we know that the restriction is tensor nilpotent. Because the restriction is tensor nilpotent, we know this is tensor nilpotent, and so that proves the statement. And then we apply Paul's result. So this is Balmer. In the paper, I think you stated it's theorem 5.4. This is in the archive version, so I hope the numbering is correct. So then the conclusion is that the homological primes for this category identify with the N prod. You get the same answer as we had before. Okay, so doing all this, you get an explicit description of what the homological primes are for GLMN. Okay. So now let's tie everything together at one. I have one last line I can put in three. Okay. So let's go back to the setup again. I have FBCH, AGFC. Okay, so where does that go to? Into the comparison, it goes to SBC of KGFC. Now, we don't have a map. We have a map to the endomorphism algebra, but we know that that's not a good map. It doesn't do anything. But we do have a map which does go from the N proj into here. And so basically, you can take projective or prime inside of there, and then you could look at the set of elements in here whose support does not contain that prime. Okay, so this is called eta. So there's a natural map which goes from there to there. We know that these two things identify. Okay, so it turns out that these two maps are basically the same. And then what you have to do to show that this is an isomorphism is you have to use realization. We use the star realization. that I stated before to show that phi is an isomorphism project. So therefore, this, we have an isomorphism here, and we have an isomorphism here. So this is what the picture sort of looks like. And I guess the last thing I want to say is the nerves of steel conjecture lives on. So I'll stop my talk.
Questions?
Yeah,
Like, for any of the primes, do you have an explicit description of what the homological residue field is?
well, just in terms of, I guess, Q points, but the answer is no, not yet, but I think it can be worked.
There's some work by Cameron and Stevenson, kind of follows I mean, in the sequence of there's newer work and those techniques might.
Yeah, I mean. It seems like it should be amenable. I mean, you can often describe it as some sort of graded comodules over some sort of tangent data.
Yeah, I could believe it. This, the nice thing about this subject is everything is very explicit. I mean, you can get your hands on it. It's like, it's linear algebra. So.
Questions? Well, let's thank Dan again.